Bismillahirrahmanirrahim. Assalamu alaikum. This is the first lecture of elementary structural analysis after lockdown, and we will be studying cables and arches. This is chapter 5 of the book by R.C. Hibbeler. You can look for detailed theory in that book as well. In this set of slides, we will have a chunk of everything. We'll not be going into the detail, but the basic theory will be discussed, and then basic problems will be discussed. First of all, we should know what are cables. Cables are often used in engineering structure to support and or transmit loads from one member to another. And while you go into the detail of the theory, you will know that cables uh, sustain or transmit the load only in tension. And we'll have two types of cases: cables subjected to concentrated loads and cables subjected to uniform loads, and differently they will be dealt. Cables are usually, their self weight is neglected when they are used as structural members in construction, but when they are used as transmission lines, then their self weight is considered. All this theory is mentioned in the R.C. Hibbeler book. Uh, when you want to go into the detail, you can go to the chapter 5 of the book. Now, cables subjected to concentrated loads. While analyzing the cables, one thing should be clear that the cables are not uh, extensible. Their length, the total length, will not be extended whatever the load is applied on that cable. So the length of the cable will remain the same overall. They are not extensible, and the cable is an elastic material. That is, when the load is removed, it will take its original shape back again, and they only support tension, no moment or shear. Now, cables subjected to concentrated loads, it means that only the point loads or the concentrated loads will be applied on the cable. It can be one or more than one. Like you can see here, it's a cable. Load is applied P1 here, P2 here. A and B are the two supports. Um, in order to uh, look for the terms that you can be using, the L1, L2, L3 are the horizontal lengths, the YC and YD are the vertical lengths, and then you have the theta. Theta is basically, it can be any angle. Here it is randomly shown for the cable if it were without any loads. When we go into the example, we will understand what does the load do and how we will analyze a simple cable with uh, point loads applied on it. Now look at this example. Here you have supports A and D. Load is applied on B and C, 3 kilonewton and 8 kilonewton respectively. The distances are mentioned. The vertical distance between A and D is 2 meters, and between C and D is 2 meters. Between B and A is H, that we have to calculate. Between B and C is not mentioned, and B and D, it is not mentioned. The horizontal distances are 2, 2 and 1.5 meters, as you can see in the figure. Now what we have to do is we have to determine the tension in cables and the dimension h. In order to determine the tension in cables, first of all, we need to see the free body diagram. If the cable was cut from here, now if you recall, while making a free body diagram, you have to see the loads and the reactions on the supports, and if any section is cut like this, what are the forces that are produced within the member. Now here in this case, TCD is the force that you can call tension as well, tension in the member CD, because it is cut from very near to the support. Now if this figure is uh, analyzed, and the moment about this point, that is point A, is taken, you will see that 8 and 3 will be multiplied by their respective moment arms or the distances. AY and AX will go into the point A, and thus there will be no distance, so they will have no effect, and we will be able to find TCD. If you see on the left side of the figure, summation MA is equal to 0. TCD is broken down into two components: TCD the X component and TCD the Y component. X component will be in this direction and the Y component will be in this direction. Now if we consider TCD the X component, there are two ways to multiply it with the uh, distance, or to calculate the vector component of the member TCD. If you recall, in the class we discussed that if there is a member um, making, this is vector, making angle theta with the x-axis, you will see that the x component is v cos theta and the y component is v sin theta. Or what you can do is you can make the 3 4 5 triangle in order to make it a right angle triangle and apply the Pythagoras theorem. In either way you do, you first of all calculate the x component or the y component of the vector, that is tension in member CD, TCD. TCD cos theta will be the x component in this direction, and its vertical distance and the distance up to the point A, which is perpendicular to the vector, will be this, and that is 2 meters. Here you can see the TCD 3 over 5. 3 over 5 you can calculate cos theta as well. If you find out the tan inverse of P over B, you can find out the theta, and taking the cos theta you can put the value here, but you can directly put 3 over 5 as well, that is equal to the cos theta in this case. So the x component of TCD is multiplied with the respective distance, that is 2. After that there is y component, it will be like this, and here you see um, the y component is found by multiplying it with 4 over 5. You can, if you have found out the theta, you can do it by taking the TCD sine theta and multiplying it with the horizontal distance, that is basically the perpendicular distance between the vector and the point you are taking the moment. Then there's the load 8 that is multiplied with 4, and the load 3 that is multiplied with the distance 2. And again, recalling the sign notations, here if you see up on point A, it has taken the counterclockwise moments positive, TCD cos theta, counterclockwise with respect to the point A, it has taken positive, and and the clockwise moments, that is for example 3 up to the point A, it is moving like this, so it is taken negative. You can take it either way, counterclockwise positive and clockwise negative, or counterclockwise positive and clockwise negative, or in any way. So if you solve this equation, you will find out the tension in member CD, that is 6.79 kilonewtons. Now moving forward, just like you solved the truss, what you did was you solve one member and then you move to the other joint. Here you will move from one segment to another. As you have found out uh, the tension in CD, that is 6.79 kilonewton, you move on point C where TBC is unknown. You can know the theta or 345 triangle. The theta BC is unknown, and there is another force 8 kilonewton. Now there are two unknowns, TBC and theta BC, and rest of the things are known. So you can apply two equations, summation fx is equal to 0 and summation fy is equal to 0, to find out these two unknowns, that is TBC and theta BC. The same procedure will be done as was done in the case of truss. That is, if you are considering for example 6.79 can be broken down into um, two components. If x component is towards the right side, it is positive, and if it is towards the left side, it is negative. Y positive upward and negative downward. And when you take the moments, you can adopt any notation, but you have to remember that if counterclockwise is positive, clockwise would be negative, and if counterclockwise is negative, clockwise will be positive. And the theta, if you want to find out the theta, the theta is usually taken from the vector to the nearest x-axis. If the vector is here, it will be taken this as theta for this member. If the vector is here, it should be taken towards the nearest x-axis, and then you can follow the simple sign notations of positive x-axis toward right side and negative x-axis toward left side, and positive y-axis on the upper side and negative y on the downward side. Anyways, solving this equation, you find out TBC and theta BC. While you are watching this video, you should have the notes with you so that you practice this example by your own self. So only then you will be able to understand it completely. Now we have found out TBC and theta BC. We have to move to the next point, that is member AB, and find out the tension in member AB and the theta as well. Here you can see that the like we used to form the joints in trusses, we have point B and its free body diagram, and the equation is formed summation fx is equal to 0 and summation fy is equal to 0, like we did up in the previous equation at point C. We'll do the same here. Find out the TBA and theta BA. Now all the tensions in the segments are found out, that is TBA, TBC and TCD. All the values of the tensions are found. The other thing that was asked in the question was the Etch distance. If you go here, is the Etch distance. It is very simple. If you know the theta and obviously you know the x distance, that is 2, you can find out the distance H uh, very easily, like it is done in this equation. H is equal to 2 tan 53.8. That is basically tan 53.8 is equal to P over B. P over B means H over the horizontal distance, that was 2. If you solve it for H, you will find out the H is equal to 2.74 meters. So that was a very simple example of cables. If you have the knowledge of solving the truss, and you have this knowledge fresh in your minds of uh, breaking down the vectors into its components and using the proper sign notation, you can solve this question very easily. Now we'll move towards cables subjected to a uniform distributed load. I will make a separate video for it so that all the topics are covered in uh, different videos, and it will be easy to find the videos after the class as well.